Perfect. I think we've done almost all of these things already. The one thing that we are going to do during this session, we are going to ask you to use the annotate feature. I think we went through all of that with you when we met one-on-one.
Can I ask you a question?
Sure. Oh, yeah.
What I wanted to find out is, should we label this as another section in our notebook?
Yep. So what I've done is I'll come up, here's like the next couple slides. So I've tried to be very concrete when it's ready to go to your notebook, and this will be another section in your notebook. Yep. It'll look just like this, direct measurements.
All right.
You're one slide ahead, Dom, but that's a good question.
Thank you.
So every time that we start a new one here, we do want you to start a new activity, and you know we've tried to make the keynotes as deliberate as possible here. So let me go back just to make sure I got everything else. So we are going to use the annotate feature again. Remember that's under. I put a little screenshot there under View Options and Annotate. So you might want to try to get there now just to make sure you can annotate. In fact, if you want to try the annotate, go ahead and you can put a stamp on my screen there or something like that on the Zoom Basics screen to make sure everybody's there. And then the most important part, again, when you're done, is you have to click on the mouse when you're done annotating. So you get control of your computer back. Last night, as Louise and I were practicing, we had, even though we met with all of you and told you all to do that, we forgot to do that, and we couldn't figure out why we couldn't get our mouse back, why the mouse stopped working. And after a little bit, we were like, moment. All right. The other things that I'm going to ask you to use during this session is probably the hand raising every once in a while, just so I can see if we're all on the same page and ready to move on. All right, now in your notebooks, if you could turn to a new page. And Louise, I'm going to ask you if you can clear the annotations for me. So there's really two kinds of measurements that the scientists use a lot when they're studying ice science. One is direct measurements and the other is proxy measurements. And I know during our pre-conversations, a lot of you mentioned that you're very interested in proxy data and how that, what is proxy data. Isotopes, I know, came up a few times. I think somebody here has a PhD in isotopic chemistry or something like that. Is that Cal? Or, so I know there's some expertise in the room, but we're going to be touching on all these. But direct measurements is probably the right place to start because it's concrete, easy to understand. So we're going to start there, and then we're going to move on to proxy measurements next. I would like to start with a little exploration. You have a tree cookie in your packet. In fact, you have two tree cookies because Louise is so nice. If you could take out those tree cookies. You guys got bigger tree cookies than me. There you go. Jim, I like it. Jim, I might need that picture later on today. There you go. I'm going to definitely need that picture after this session during the break. So here's the way that we're going to explore these tree cookies. I'm going to ask you to put down in your notebook two things at least underneath each one of those two headings. So at least two. You can stop when you get to 5, but I'd like you to look carefully at those tree rings and write down 2 to 5 things that you notice about the tree ring itself when you look very carefully at it. So these are direct things that you can observe about it. And in the other column, I'd like you to put down 2 to 5 things that you wonder. So if when you're looking at that, a question comes up, put that down in the I wonder column. And that is awesome. Somebody's already annotating. We can do that. If you want to use your annotate feature, go ahead and write on there. You can go ahead and type a few things onto the screen itself.
For anybody who can't annotate, if you want to send me a message, you can write it in the chat box and I'll try to annotate it for you.
You can use my classroom ideas page also there. Yeah. Feel free, if you're adding your annotations, you can put it on top of the I wonder too. You can find some blank space there. All right.
Bill,
Yes.
is this going to the text? My text went on the other people's, or colleagues' writing.
And Rose,
I am sorry. Yeah.
yeah, I'm struggling. Louise, I don't know if you can move those annotations since you're a host. I'm struggling on my own computer right now because when I go into presentation mode, I lose my mouse on the screen where it is. So I'm having a hard time moving things myself.
Okay. Thanks.
Move those. But those are great, great questions. And what I found, if you give kids a voice, a lot of times they'll drive your entire lesson, and all of the things that you want to actually teach will end up coming from them, which is really kind of nice. And we're going to answer some of these questions right now. So I had actually intended you guys to all annotate on this screen, but you guys started annotating before I could even get to it, so which is okay. But I was going to put all the annotations on this one screen about what you notice. But you do notice a lot of good things. One has more rings than the other, yes. There are wide rings and there are narrow rings. That's a good question. And then some people wonder, why are there wide rings and why are there some narrow rings? There's a good reason for that. We're going to talk about that today. The dark part, why is there dark part and which part shows growth? Those are all great things to notice, and those are all great things to wonder. We're going to talk about all of that. So Louise, if you could clear that annotation for me again, that would be great. So I just want to define exactly, so we're all on the same page, what direct measurements are. Direct measurements are simply things that you can go out with your instruments and measure directly, hence the name direct measurements. For example, a rain gauge is a really nice example of a direct measurement. I put the rain gauge out in back of my yard, it rains. When the rainstorm's over, I go out, I look, it rained 2.5 inches, boom. That's a direct measurement. There's no ifs, ands, or buts about that. No interpretation, no plus or minus. That's what the measurement is. Other examples of direct measurements, when you hear carbon dioxide measurements, That is an example of a direct measurement. If you know this website, co2.earth, I used to have that website up every day in my classroom, just when the kids came in. co2.earth, great website. It actually shows the daily live direct measurement of what the carbon dioxide is. So you can see I first put this presentation back together in April. On April 22nd this year, it was 415 parts per million. A year ago, 414. It's concerning. I'll never forget the first day that I realized it went over 400. I was trying to calibrate my carbon dioxide sensor. Veneer makes some nice carbon dioxide sensors for your classroom. I was trying to calibrate it and it kept coming up over 400. And I'm like, wait a minute, no, it should be like 390 something. There's something wrong with this. And I kept looking and looking, and then I logged on to co2.earth, and all of a sudden I was like, oh my gosh, this thing is reading correctly. We've broached 400 and now we're coming up on 420. So anyway, those are direct measurements. Let's also talk about just some direct facts about tree rings. These were some of the things that you wondered. That middle part that looks different on your tree ring, that is actually called the pith. We're going to actually be focused on the other part outside the pith. These are called growth rings. And the very outside part there, that is the bark. So that lighter colored part of the tree ring, that is where the tree was growing in the spring and early summer. And the dark colored there is where it's late summer and fall. So it does grow in the fall, but most of that growth of the tree, it's amazing, happens in spring and early summer. So if you learn nothing else today, it's really important to fertilize those trees right before the snow melts if you live somewhere where it snows, because right when it melts, that's when the trees are really going to take off. Doesn't do a whole lot of good to fertilize later in the year. But what you need to know for this activity is this, is one light band and one dark band, that encompasses 1 year of growth in that tree. So if I'm counting growth years, I would count it like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are the basic facts you have to know to make some direct measurements on this tree.
Bill, can we actually make it easier and just count all the darks and then multiply by 2, or it is by equal to 1 year, instead of going every lighter?
Whatever strategy you want, Rose, is fine with me.
So Bill, either we can count the dark color or the light color. The dark and the light represents a year, right?
I would love to have students having that conversation. And if you're having that conversation, then you understand about tree rings, because there's a lot of ways to get the right answer. Because here's what I'm going to ask you to do. I'm going to ask you to come up with a consensus on how old or how many years of climate data are in this. So I'm going to ask you to count in a second, Rose, for me to, but hold on 1 second, because first I got to define this, because this is a word that sometimes is misunderstood. Consensus. I actually looked it up in the dictionary to make sure I had the right definition. A consensus is a general agreement. I think sometimes people confuse consensus with a unanimous decision. All right, 2 completely different concepts. We're going to ask you to come up with a consensus. For example, there is scientific consensus that humans cause climate change. All scientists know, 97%, but that's high enough that we consider that a consensus. I don't know where the line is. I would think the 3% of scientists who don't believe that climate change, that would not be a consensus, the 3%, but the 97% is definitely considered consensus. So we have about 12 of us in this room, and I'm going to ask you guys to collect some direct measurements here and come to consensus.
Are we looking at your picture or are we looking at our own sample?
That's a good question, Rose. And here is the answer for that. Because everybody's got slightly different, we had hoped that if I was doing this in my classroom, sometimes when you order these, you can actually get them all out of one tree so they're all exactly the same. So you would know that the kids all have the exact same one. Or if you cut down your own branch out in your backyard, you can cut your own tree slices and have them look at your own. We all have different ones. So I would like you to use the one that's on your screen right now. And I would like you to use that annotate feature again and see if we can come to consensus. Can you decide how many years of climate data are captured in that tree? And when you think you know, when you think you have your count, can you put your number using the annotate up on that tree ring?
Well,
Go ahead, Rose, I'm listening. Nope, I think you froze, Rose. But when you come back, feel free to ask whatever it was you were gonna
yeah.
ask.
How does the bark count?
Oh, see that's a good question. I don't know for sure the answer to that question. I suspect the answer is no, the bark does not count because the bark kind of forms in that first year, so it would be included in there. Karen's saying, no, 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 she must know more about trees than me. Yeah. So with those numbers on there, what could you say about a consensus that we've reached? Is it possible to reach consensus with the numbers that you guys see on your screen? Feel free
Looks
to.
like majority of us pick 17.
About 17?
Let's look that way.
Sure. And see, now is where you might want to throw in that plus or minus. So we can say, hey, we've reached consensus that this represents about 17 years of climate data, plus or minus 1 or 2 years.
1 year. Mhm.
See, so I think that's important to teach the kids also that real scientists don't have an exact number sometimes. They have to struggle with these measurements, even with direct measurements. It seems like this should be super easy. I mean, hey, it's just a tree. We all should be able to come to consensus on that. And here's a group of really experienced people and we're all getting different numbers. So one way to do it is you all get back together and you go fight about it again. You say, no, it'd be really nice to say who got 15 and who got 18. Let's get those people together to talk and see if we can at least eliminate those outliers and then start working our way towards a more refined number. But that's a really nice activity you could do with your kids just to show your kids a little bit that science, all these numbers that they come up with, it's not necessarily cut and dry. They're actually coming up with a range of numbers. And then all these real scientists in the polar regions are fighting about what the real number that they should publish is. You're going to meet a guy named Eric Osterberg later on. And it was amazing how he stressed the fact that this is exactly what they do when they're doing real science, is they all come up with different numbers and they all get together and start fighting over who's right and who's wrong and how, what kind of bands they can put on it. So a nice activity for your kids, very simple, cheap materials, just to expose them to what direct measurements are. Any questions on the tree ring before we go on? Yeah, Cal.
Well, I was wondering about the thickness of these rings. Do they mean something? Are they related actually to the productivity of the trees, like photosynthesis, net primary production, all this stuff? Are these the thickness? I see like different thickness, variation in the thickness. Another question is, dry and wet seasons, because we're talking about climate change. Can we identify the dry and wet season from the tree rings? Thank you.
See, so Kel, you're really asking a couple different things there, and let me answer your question and put your question off, both. To answer your question, when you're asking, is it dry and wet? There's really no way to look at a tree ring there and know for sure if it was dry or wet that year. Now, there is a way to look at it directly and count how many years there are. So that's called a direct measurement. What you're asking is, could we come up with the width of a tree as a proxy for if it was dry or wet? So you'd really kind of be saying, you'd have to kind of do some statistical studies and say, hey, let's look at all the wet years and see how wide those rings are. Let's look at all the dry years and see and see if there's a relationship first. If we do find a relationship, that relationship we could then call a proxy for if it's dry or wet. So when we actually, that's to answer your question. To not answer your question, I'm not going to tell you the answer to that, but I will show you some data that relates to that so you can see that for yourself tomorrow. Actually, precipitation and the widths. So that'll get you back tomorrow. So, all right, let's keep going. Let's make another direct measurement. You also got this really cool ice core. And Louise, I'm going to ask if you could clear my annotations again, and hopefully by tomorrow I'll be able to clear my own. You got a model of an ice core here. This is like one of the coolest things. The only way it can be better is if you give it some light. So you also have a closet light from Home Depot, and you're like, why on earth did they give me a closet light from Home Depot? Well, if you put on the closet light and put it underneath it, then the bubbles come to life, and it's like, ooh, glowing bubbles, yes. So we actually presented at AGU, the American Geophysical Conference in San Francisco last year, and we had some of these ice cores just sitting on the table with the lights underneath, and we had a little cover over the light so you couldn't see it. We were like the most popular booth there because everybody came over there like a magnet. Oh, let me see the bubbles. They all picked it up and wanted to talk. So if you want to get your kids involved, just have this sitting on the front table when they walk in, and it's going to be, ooh, you know, I see glowing bubbles, you know. So anyway, but this is a nice model of an ice core. Now, every model has strengths and weaknesses, but on the outside of this is actually a photograph made into transparency and taped onto the outside of that ice core. So it is pretty realistic. So when they go to get these ice cores, and we're going to talk to the scientists and engineers who go to get these and have been down on the ice actually pulling these as the week goes on. Some of the drills they use are medium sized like this one. Some of them are much smaller. But they all do the same thing. They pull out this core of ice. The standard size core is about 4 inches in diameter. Then those ice cores get transported from Greenland or from Antarctica all the way back to the United States and stored. It's actually stored very close to Matt in Colorado. That's where one of the ice core centers are. There's also one on the East Coast. You're going to meet one of the scientists who works with the ice core storage facility on the East Coast. And a lot of these labs like Dartmouth, they have their own storage freezer. You'll see Dartmouth storage freezer for where they keep their ice cores later on too. So in your notebook, I'd like you to do that same exploration again, except this time I'd like to explore this ice core. And could you put I notice and I wonder in your notebook for the ice core? And let's just, I like the way you guys annotated. I wasn't planning on you annotating on this screen, but I like that. But see if you can guess either on the left or right-hand side of my page where somebody is not going to be typing. And go ahead and write in your own notebook 2 to 5 things that you notice, and then go ahead and type 1 or 2 things on the screen. And again, just somewhere on the left-hand side of my screen, somewhere on the right-hand side. It doesn't have to be underneath my T-chart. Mm. So I appreciate those questions and comments. You're noticing, I wonder, little sidebar here. Remember, Louise, one of the things in the fine print was you can get class materials, up to 3 sets of class materials at the end of this. So if you like these cool things and you want a class set so all your kids can get their hands on them at the end of this workshop, you'll be able to tell Louise, hey, send me a class set of these, or if you want a class set of these. Um, so those are, again, great questions, and we're going to address some of those right here. Louise, if you could clear my annotations for me again, that would be appreciated. But here's what a real ice core looks like. So the blue coloring on this one is kind of a strength of this model and kind of a weakness. The real ice cores don't look blue like that, but the glacial ice, when you look at a glacier, they do reflect blue. So if you've ever had the opportunity to stand on a glacier, when you look down, it actually looks that blue color. The ice cores don't, but the blue is a false color that helps you see things a little bit better in there. So that's why the blue coloring is on this ice core. So what I'd like to ask you guys to do is collect some direct data on this ice core. But again, here are some facts about these ice cores that you probably have to have in your mind before you can actually start to collect some direct data. So fact number 1 would be this. If you notice, there are some lighter colored layers in there. And this is a lot like the tree rings. There's some overlap here. So anytime that the snow is falling in the spring and summer, it forms this kind of light colored bands. And those dark colored bands is all snowfall that's accumulating in the winter. So if you know that, then you can start to make direct measurements as to the age of the ice or how many years of climate data you're actually looking at. So if I count, any way you want to do it is up to you, but one light band and one dark band together, that is 1 year of climate record in the ice core. So asking you guys to make your own direct measurements then. My question is, with your own ice core that you're holding in your hands, could we come to consensus on how many years of climate data are actually captured in this model ice core that we sent you? So go ahead and try to make that direct measurement. And when you're done with that direct measurement, go ahead and type your answer onto the screen and we'll see if we can reach any kind of consensus on that. I see 32, but I need better glasses. So I don't have an answer for this. I haven't counted myself, but I do see two very distinct different types of answers on my screen right now. I see one group of people that's coming in the range of about 17, 16, 18, 19, so somewhere in the teens, and I see another group that's 30 to 40. So those are two very different answers. Can you guys unmute and chime in, and let's see if you can make an argument for one way or the other, and just like if you're in the 30 or 40 group, can one of those people kind of tell how you got it? And somebody in the 16 or 17, 18 group, can you guys also chime in and tell us what you were thinking?
Can I just speak from my choice? I selected 17 or 18, and the reason is that one white and one dark band is that's what my understanding. So it was counted as a combination, like, so that's how I got 18.
Anybody else? Go ahead and chime in here.
Go ahead, Dalton.
I think that basically it's really hard to tell because there's overlap between the layers. They sort of blend and they're not as distinct as tree rings. So I think for me, I put 16, but it could be more. It depends on the clarity of it.
I think there's a lot of variation in the winter snow thickness. So for me, I was a 33 there. It was, it had to do with basically trying to guess whether I was looking at one very thick band or two, you know, basically if there was light in between it, I split it. I didn't consider it to be a single band of winter snow.
So what I would really like to do is send one of these to Eric or one of our ice scientists that are coming in later, and because we really have two different camps here. We really have a camp up around 30 or 40 and a camp down around 17 or 18. Louise, what did you count? You've done this more.
I was in the lower amount, but I definitely waffled on a few of them. This is actually a real ice core. This is the GISP 2 project, which is Greenland Ice Sheet Project, the second big core. So it's a real core, and my guess is Eric could help us out with that tomorrow. We could ask him how you do that.
So for this next one, then we're going to have two different conclusions then as we write it, because I am going to ask you to write in your notebooks, I'm going to ask you to write a conclusion. So it looks like we have one group of 16 to 19 and one group 32 to 46. So I'll let you write your own conclusion in whichever camp you are, and when Eric comes in, we're going to try to get him to weigh in on how many years it is. But I'd like to give you a tool to use with your kids that maybe will help them with their writing skills to be able to express their scientific thoughts. I actually picked this up. This was not my idea. I picked this up from a friend of mine, a guy named John Lewis. And I don't think it was his idea either. He just brought it to light and helped me implement it in my own classroom. But this, if your kids are anything like my kids, they struggle with writing. And they struggle with writing in a scientific way, especially. And this little technique changed my classroom completely last year. With claims and evidence, just starting their conclusion with this phrase, the data suggests. And once you become aware of that and start using that phrase in your classroom, you'll start to hear it all the time. I heard it on the news numerous times in the last week, where scientists are being interviewed, or even with all the racial unrest and the statistics that are out there right now with that. I've heard numerous people start citing their statistics with the data suggests, and then they would go that way. So it's a very powerful statement. And the thing that's really nice about it is it frees you up from having to be correct. It allows kids to just say, hey, these are the numbers that I see in front of me, and this is what it suggests to me. And because they don't have to be necessarily right or wrong, it seems like their writing just exploded and they were much freer to just write it. So here's what I would like you to do, is I would like you to answer that question on the top. And the question there, which climate record, the tree slice or the ice core, captured a longer span of the Earth's climate history? So in your notebooks, you should have how many years of data were in that tree ring that I had up there, what we had consensus. And you also have in your notebook how many years of data you counted in the ice core. So I'd like you to write a two-part little statement to summarize this activity. I'd like you to finish the first sentence, the data suggests, and tell me which one you think captures the more of the Earth's history, climate history. And then the second part of that, you have to back it up with some numbers, some data that you collected using your direct measurements. And then I'd like somebody that's really brave to actually type it using their annotate tool, whatever they got written in their notebook, over on the left-hand side where I have classroom ideas, so we can look at how you use this format with this question.
Are we taking picture of this?
Oh,
Or we are just going to write it on the screen?
Oh, I would write it in your notebook. I would ask you to, Rose, just practice once and write it in your notebook. And then if somebody's done and they're brave enough to share theirs, I'd ask that somebody share it with the annotate feature on the left-hand side where I got lots of room to write there.
We can't remember the citations, but we read this information for our students for the class. Like, do you need something like this? Because I can't remember the citations.
I'm not sure I understand your question about the citations, Rose.
So we are getting this conclusion based on our experience right now, or all the materials that we cover in the class, because there are literature that actually provides the answers.
Oh, no. So I'm asking just about this sample of ice that you had. So like this ice core.
Oh, I see. Okay.
To the tree ring, you know, which would have been this tree ring, but the one that we looked at on the screen. So just which is capturing a longer period of the Earth's history, this ice core or the tree ring that we looked at on the screen.
Okay. Thank you.
Yeah, and there's a conclusion. The data suggests the ice core is older than the tree because evidence that supports this is there are more bands of ice. So what I would ask in that conclusion, if it was my kids, I would almost ask them to say, well, you just backed up a claim with another claim that there's more bands. I would like to see a conclusion that has the claim on the front end and actually numbers from the direct measurements you made on the back end. So instead of supporting a claim with another claim, back up that claim with actual numbers and evidence. So thank you, whoever typed that in there. Awesome, thank you. There's no names on it, so we can't judge. But if somebody else could type in, let's try another one, and let's just see. This is just teacher to teacher. You know, the way that you can help your kids improve their writing around something in this case, which is climate. But I like the way that that first one they did. They started with the data suggests. And when you do that, it's all of a sudden, it's a nice little sentence starter for them, and it's a way that they can write it. So if somebody's brave enough to type their conclusion in and make sure that the evidence statement actually has some numbers in it from the data that you collected, that would be awesome. Louise, can you move that one annotation there? The one just got overlapped. You can't move it?
No, I'm not able to move it for some reason. I can clear them, but I can't move them. Yikes. Oh. Can you move it when you're off screen? I mean, when you're not sharing?
Let me see.
It's interesting that it's behind it.
Yeah.
Huh.
So at the very bottom part was I wrote, I remember what I wrote. Maybe the person who wrote on top of what I wrote can say something. It is okay, we are learning after all.
Yep, we're learning, yep.
Yeah.
Rose, what did you write? Go ahead.
Well, I said evidence, so based on that small portion of the ice that we were actually debating how many bands, it shows us that even that smaller portion of ice, we are having more bands, and it is seems to be a lot, you know, a lot more. It could be a lot more because it didn't look like it was a whole stretch of the ice core itself. Like I was thinking that was just a sample.
So I love exactly what you said, and your arguments are all solid, and all those are good claims. But what I would challenge you with, to challenge your kids, is to support those claims with numbers. So what I would be looking for in the evidence statement, Rose, is when you say there's more, like to be able to say, the evidence that supports this is when we looked at the tree, it had 18 years. When we looked at the ice ring, we interpreted it as only having 13 years. Then there's actually numbers there to back that up as an evidence statement.
Right. Okay. Yeah.
Kids struggle with that because they want to make a claim on top of a claim. And I think right now, just scientific literacy, it's really important because we live in this environment where people put claims up about everything. You want to see the numbers behind that. So somebody might claim, for example, in this one, somebody might say, hey, the data suggests the tree, has a longer span of the Earth's climate history than the ice. The data that supports this is the tree was 16 years, the ice was 15 years. Well, if I saw numbers like that, then I could look at that critically and say, wait a minute, 15 and 16, that's only 1 year off. Do you really, what's your data spread on that? And are those really the same number or not? But now you can start to have a much higher level of conversation about that data once you see those numbers.
Bill?
Yeah.
Yeah, this is what I have for that second question. I just put the evidence supplied is derived from the consensus of the group, finding the ice core appears to cover 20 to 30 years of time, as opposed to tree rings covering approximately 12 to 16 years.
And that, I would say, Don, that is a great evidence statement that has numbers and data to support the claim you made. How did you write the first part of your sentence there,
First
Don?
part, I just have the data collected suggests that the ice core appears to have covered a larger span of time than the tree cookies. That was all I said. The first part.
You're using this tool in a great way then, Dom, yes. And I would say that if you provide this to your students and you're patient with it, you will see their writing be able to explode. If you ask them open-ended questions like this, I think there's another thing just teacher to teacher to look at here. And that is the question that I asked is actually an investigable question. So I would like you to just look at teacher and reflect. I mean, this isn't just teaching climate change or anything, but are the questions you're asking your kids investigable, or can they just answer it with a simple yes or no? Because the way that this question is phrased, you really can't answer that question with a yes or no answer. So as a teacher, sometimes the biggest challenge for you is to put that question together so that kids can't answer it with a yes or no, and it leads to an investigation. Because this simple little question leads to an investigation. Now I have to take my tree core and ice ring and actually collect some direct data, and then I can answer that question. So that would be a teacher to teacher kind of moment there. So any questions or comments about that little activity, and then we're going to begin the transition away from it. I have a couple other things to show you.
How would you state the claim? If you were, I mean, if you were modeling this, what would you say in terms of opening with the claim and then the supporting? I get the supporting evidence, but what?
Hey, Dom, can you restate the data suggest again?
The first part?
Yeah.
The evidence.
The data suggest.
The evidence. Okay, the evidence supplied is derived from the consensus of the group finding ice core appears to cover 20 to 30 years of time, as opposed to the tree rings covering approximately 12 to 16 years.
Perfect. Leanne wanted to hear the first part of your statement instead.
Oh, you want to hear that too? The data collected suggests that the ice core appears to cover a larger span of time than the tree cookies.
And Leanne, that to me would be the claim. That's their claim. Again, I think the three takeaways there are: number one, try to phrase a question that's investigable, that leads to the students actually collecting some data. Number two, that investigable question can't be answered with a yes or no. And then give the students some framework, some scaffolding that helps them start to express their own ideas. And this little phrase to start your conclusions with the data suggests and giving them evidence that supports this is a really nice way to do that. And again, depending upon your kids and their ability and levels, you know, I worked with kids that were 12 to 15 on their ACTs, and I worked with kids that, you know, were the 36s that had offers from all over the country. And so the amount of scaffolding that they need is different. So sometimes, especially depending upon how you process things in your class, if they have labs that they have to write up, what I liked about Google Docs is when the kids needed scaffolding in their conclusion, if they had to type something for me and turn it in, I could actually put these sentence starters on there, and then they could build on that sentence starter. And then I could slowly take that scaffolding away as the year went on. But, all right. Let me wrap up with one of the questions that came up. I think somebody was alluding to this. And I'd like you to use your annotate tool again. And this time we're just going to use the stamp. You're going to vote with a stamp. But here's my question to wrap this one up. If we look at trees, all of the trees that they've made direct measurements on the planet, and if we look at all the ice cores that they've drilled and made direct measurements on and counted up, how many years? That is the question that I would like to know, is which one of these two sources of direct measurements for age has a bigger view back to see what the climate history of the planet really was like. So you do have to vote, take a stamp, and put a stamp above either the ice core on the screen or put a stamp above the tree core on the screen.
Bill, you have to share your screen again.
Oh, I'm teaching away here and I'm the only one looking at my screen.
That's why there's two of us.
Thank you. There we go. That probably makes more sense now.
Except
And I
you're showing,
apologize before
you're
Leanne,
showing
'cause
your presenter slides, Bill.
you got my presenter slides up?
Yep.
What in the world is happening? Good thing we practice so much. Five, six. We need a few more votes out there. Ice Ice Baby. There you go. It's going to be a good group, Louise. All right. So if you chose the tree, I see a check mark and a couple others on that side. That is a good guess because they actually have tree records going back 13,000 years. And that's not a 13,000-year-old tree, but that's by overlapping the tree that's growing in your backyard right now with the one that's dead, with the next one that they find, the next one. And they can actually go back 13,000 years into the climate record using trees. However, if you did choose the ice, it's not a bad guess because, yeah, they go back 800,000 years of ice. So a continuous record, almost a million years into the Earth's climate history from the ice cores.
And recently they found a 2.7 million year old piece of ice. But that's going to be the next science question is how do you get a continuous record back farther than 800,000 years?
So I apologize that my screen wasn't sharing there for a while. Let me go back here and just wrap this up. So Leanne, was this up at all? Was this on the screen before when I was talking? Okay, okay, good. I just didn't want to make that I was just talking to myself and the only one looking at it. All right. So with that said, we have about a 10-minute break here again where you can get up and stretch. All of these will be linked on your syllabus. One of the things Lauren is going to do is she's going to go back and link all these keynotes and all the actual labs. There's actually a lab handout, about a 20-page lab that goes along with this activity that you can download off the icedrill.org website and use in your classroom. It's got student sheets and everything else. It's much more probably structured than what we did because it's hard to put kind of unstructured stuff like that into words, but it's all available and you can explore that later on tonight.